It's May the 11th, 1997. Garry Kasparov, arguably the greatest chess player in history, just resigned after only 19 moves. His opponent? Deep Blue, IBM's chess-playing computer. Kasparov later said he felt something strange across the board that day, a presence, an intelligence unlike anything he'd encountered before. The whole world watched as a machine defeated a human at what we considered our game. Pure intellect, pure strategy. But here's the thing, while everyone's cameras were pointed at that chessboard, a completely different revolution was happening. Quieter, way less dramatic, and honestly, far more important. This is the story of how AI finally started working. Not through big promises or fancy hardware, but through data, patience, and learning from experience. Okay, so let's talk about Deep Blue for a second, because it's actually really important to understand what this thing was. Deep Blue was incredible. It could evaluate 200 million chess positions every single second, using 256 specialised processors working in parallel. It had extensive opening strategies hand-coded by grandmasters, massive endgame databases, position evaluation functions. I mean, this thing was the peak of what you could build with pure computational power and human expertise. And it worked. Deep Blue beat Kasparov 3.5 to 2.5 in their final match. Genuine achievement. But here's what nobody really talked about at the time. Deep Blue was a dead end. It couldn't learn from its games, it couldn't improve through experience. It couldn't take what it knew about chess and apply it to anything else. Not checkers, not Go, nothing. After each game, human programmers had to manually go in and adjust the evaluation functions. Deep Blue represented symbolic AI at its absolute peak, and at the same time it showed everyone exactly why that approach had fundamental limitations. While Deep Blue was making headlines, a different group of researchers was making quite steady progress with something fundamentally different. They weren't hand-coding knowledge, they were letting systems learn from data. The shift was as much philosophical as technical. With traditional AI, you'd interview experts, extract their knowledge, encode it as rules, and build these rigid systems. With machine learning, you collect data, design algorithms that can spot patterns, and let the system learn through experience. And this started showing up in some very unexpected places. In 1998, two Stanford grad students, Larry Page and Sergey Brin, launched a search engine called Google. Their big innovation wasn't hand-coded rules about what makes a good web page, it was PageRank, an algorithm that let the structure of the web itself determine what was relevant. If lots of important pages linked to your page, then your page must be important too. Meanwhile, their competitors like Yahoo were literally employing human editors to categorise websites. Humans sitting there organising the internet by hand. By 2005, Google was processing 200 million searches daily. The data-driven approach had won decisively. Similar thing happened with email. Early spam filters used simple rules. For example, block messages containing the word Viagra, block certain domains, block specific patterns. Spammers adapted immediately, replaced Viagra with V1 Agra, used new domains and changed the patterns. It was an arms race that rule-based systems just couldn't win. Then in 2002, programmer Paul Graham published an influential essay about statistical spam filtering. His idea? Instead of rules, train systems on examples of spam and legitimate email. Let them learn statistical patterns, let them adapt automatically as spam evolves. Within a few years, statistical filtering became standard across all email systems. The difference in effectiveness was dramatic. So you're starting to see a pattern here, right? Across completely different domains, search, spam filtering, you name it, systems that learned from data were outperforming systems built from hand-coded rules. And three things made this transformation possible. First, data abundance. The internet was generating exponentially growing amounts of digital data. By 2000, humanity was generating more data every single day than existed in all recorded history before 1995. Every search query, every click, Every online interaction was creating training data. Second, better algorithms. The 90s and 2000s saw fundamental advances in machine learning techniques. Support vector machines in 1995 for classification problems. Random forests in 2001, which combined multiple decision trees. Boosting algorithms that could improve performance iteratively. These weren't just incremental improvements, they were mathematically rigorous, theoretically sound, empirically validated approaches. Third, Moore's Law. While AI went through its winters, Moore's Law just kept chugging along. A typical computer in 1995 had 16 megs of RAM, a 1 gig hard drive and a 100 MHz processor. By 2005, 1 gig of RAM, 100 gig hard drive and a 3 GHz processor. That's 60 to 100 times more powerful. When these three forces converged, abundant data, sophisticated algorithms and sufficient computing power, machine learning started delivering real practical results. By the mid-2000s, machine learning was quietly everywhere, and I mean everywhere. Credit card companies were using it for fraud detection, analysing billions of transactions, learning normal patterns, flagging weird stuff in real time. Banks were using neural networks to read handwritten checks, a problem that had seemed basically impossible just years earlier. Digital cameras started incorporating face detection, automatically identifying faces for better focus. Pandora's Music Genome project used machine learning to recommend songs, analysing musical features and what you actually listen to. Google's AdWords matched advertisements to search queries using machine learning, creating a business model worth billions of dollars. Amazon's customers who bought this also bought drove huge revenue through learned patterns of purchasing behaviour. Even autocorrect on your phone was learning from usage patterns, trying to predict what you meant to type from your imprecise touchscreen mashing. Here's what's interesting though, none of this was called artificial intelligence. The term was still professionally toxic after 2 AI winters. Instead, researchers called it machine learning, statistical learning, data mining, predictive analytics. Same techniques, different branding. But it was finally working. In October 2006, Netflix announces a competition, $1 million to anyone who can improve their movie recommendation algorithm by 10%. Over 40,000 teams from 186 countries competed, and this competition revealed some really important patterns. First, ensemble methods combining hundreds of different algorithms outperformed any single approach. Second, data quality mattered way more than algorithmic cleverness. More data with simple algorithms often beat sophisticated algorithms with less data. Third, those last few percentage points were extraordinarily difficult. Going from a 9% improvement to 10% took years of additional work. In September 2009, a team called Bell Calls Pragmatic Chaos, which was actually multiple research groups working together, achieved 10.06% improvement. The irony? Netflix had shifted focus to streaming video by then, and the solution was never actually deployed. But the competition's impact was huge. It demonstrated machine learning's commercial value, popularised ensemble methods and collaborative filtering, and helped establish Kaggle-style competitions as standard practice in the field. The Netflix prize happened right as big data was emerging. This recognition that massive datasets fundamentally changed what was computationally possible. In 2009, Google researchers published a paper called The Unreasonable Effectiveness of Data. They showed that simple algorithms on enormous datasets often outperformed sophisticated algorithms on smaller data. Technologies like MapReduce and Hadoop made processing these massive datasets actually feasible. And here's where things got interesting and a bit uncomfortable. Data itself became a competitive advantage. Companies that collected more user data could train better models. This created a dynamic with some very significant implications that we're still grappling with today. While all these practical applications were proliferating, foundational work was continuing in universities. At Stanford, computer scientist Fifi Lee recognised a critical limitation. The datasets everyone was using were too small. She envisioned ImageNet, a dataset containing the entire visual world, properly labelled and freely available to researchers. Using Amazon's Mechanical Turk platform for crowdsourced labelling, her project assembled 14 million images across 20,000 categories. In 2010, the ImageNet Challenge launched as an annual competition to build the best image classification system. Early results showed about 74% accuracy using traditional computer vision techniques combined with machine learning. Progress was steady but incremental, just a few percentage points improvement per year. Meanwhile, a small group of researchers kept working on neural networks. Geoffrey Hinton in Toronto, Yann LeCun in New York, and Yoshua Benjo in Montreal. These guys had persevered through 2 AI winters when everyone else had given up on neural networks. In 1998, LeCun's LeNet was already reading bank checks, proving that convolutional neural networks could work in practice. In 2006, Hinton introduced deep belief networks, showing how to train deeper neural networks through this technique called layer-wise pre-training. Then in 2009, researchers discovered that graphics processing units, or GPUs, the same chips used for gaming, could accelerate neural network training by 10 to 50 times. By 2012, every ingredient was in place. Massive labelled datasets, mature neural network techniques, GPU acceleration making training feasible, infrastructure for distributed computing. The period from 1995 to 2012 saw machine learning transform from a research curiosity into fundamental technology. But here's what made this different from previous AI booms. This advancement proceeded quietly. No grand promises, no excessive hype, no claims about imminent general intelligence. Researchers just delivered practice results, published empirical evidence, built working systems. Companies adopted machine learning because it worked, not because of speculative potential, but because of demonstrated value. The field had learned from 2 brutal AI winters. Be patient, be rigorous, be honest about limitations, deliver incremental value. And then in September 2012, at the ImageNet competition, a team from Toronto submitted a deep neural network called AlexNet. They won by 10.8 percentage points. Not a close second place, complete obliteration of the competition, and everything changed. In the next episode, the deep learning revolution. 1. AlexNet's breakthrough. 2. AlphaGo's triumph over the world Go champion. And 3. Generative adversarial networks or GANs creating photorealistic faces of people who don't exist. And the 8 years that transformed AI from a useful tool into a transformative technology. If you found this interesting, hit that like button, it genuinely helps the channel to grow. And subscribe if you want to know when the next episode drops. It's completely free and you'll be along for the ride as we continue this journey through the AI story. I'm Ian and this is AI Scrutinised. Thanks for watching.